Welcome to the 2020 Third International Conference on Economic Development and Green Development. And I'm Mike Lyons, Adjunct Professor in the Stanford School of Engineering. And today we're going to be talking about DER, Distributed Energy Resource Applications for storage in microgrid deployments. And so we'll be getting into some details around the difficulties of doing some of those deployments and, of course, why they are so important. So let's talk about the major points we're going to try to make in this discussion today. First of all, why is distributed energy resources important? Well, the obvious one, of course, is dramatic reduction in greenhouse gases. Without deployment and adoption of DERs, we're going to have increasingly difficult times in deploying renewables that will allow us to reduce greenhouse gas emissions and hopefully reduce global warming impacts that are so much in the news these days. And the obvious question is, well, what's the problem? Why don't we just build more wind farms and more PV installations, connect them up to the grid, and we're done? That's all there is to do. Well, unfortunately, it's not that simple. And integrating intermittent energy sources like renewables into grid deployments can be extremely tricky. And in order to do this effectively, as we'll see, energy storage is absolutely required, and there isn't nearly enough of it right now. So let's talk about what some of the key issues are in deploying DER and what are the current approaches that are being looked at right now. So if you want to look at trends, one of the good places to go is the California Independent System Operator, CAISO, and they have some interesting challenges that are going on. And as we'll see, California has a mandate for some fairly dramatic increases in DER adoption over the next few years. And along with that, there's a real grid stability issue. And in order to make that work, we need some very low latency controls for some of these hybrid grids. We'll talk about that more in a minute. And that ties right into the whole communication, command and control SCADA problem for high reliability architectures. And these kinds of tools and applications already, thankfully, exist and are well proven. And we'll talk about that as well. And at the end, we'll mention some advanced energy storage concepts which can be used to help us out as we drive for higher DER adoption. So on the trend side of things, one of the big factors here of interest is the behind the meter market segment. And what do we mean by behind the meter? This is essentially everything that goes on in residential and office deployments, structures, and so on, where the amount of energy that outfit uses is being measured by some kind of meter. And usually these days, these meters are so-called smart meters, which are taking a lot of data about the energy that's being used, and in some instances, ways of actually controlling how it's used inside of a building. There's going to be a big boom. This has already started in some markets where energy storage is actually going in behind the meter. And in smart applications, it means that the grid operators are going to be able to access that energy storage system via these smart meters. This means that dramatic escalations and energy storage capabilities will be occurring at the local levels. And so it won't just be energy storage that's sitting at a wind farm, for example. It will be fully distributed potentially throughout an entire region. This is going to be potentially a very efficient and cost-effective way of doing this and also, accessing things like unused electric vehicles and things of that nature. So one of the big problems in deploying DER is grid stability. And as we see more and more small grids, microgrids, and so on being used at the local level, these things have to be integrated in and talk to very effectively the main grid. And in order to make a lot of this grid stability stuff work, we need more storage, because otherwise there's no easy way of managing the energy in the microgrids and in the larger grids. As we can see here, California has mandated that 50% of power generation is going to be DER by 2025. This is a very, very aggressive goal, and storage is going to play a key role in making that happen. One way of looking at this storage situation is California's famous duck curve. The reason it's called a duck curve, you'll see in a minute, is that it looks like a duck in terms of its shape. And this is being caused by increasing deployment of solar power installations, and as well as wind farms. And so this really has to do with over generation and the management of the same thing. So what the independent system operators have to do on a minute by minute basis really is balance the power that's being generated versus what's being consumed. Very much in a continuous, essentially real-time way. And in order to do this, right now, it's not effective to distribute a lot of this over-generated power using transmission capacity into other areas that could potentially use it very efficiently. The transmission capacity is very poorly built out, very poorly developed, and it's one of the key elements of why DER is not being properly deployed. So one way to get around that, of course, is to go to local distribution and more storage. One of the characteristics of this is that storage adoption and deployment is going to improve simply because battery costs are dropping. Now, this really means to most of us that distributed energy storage, especially this behind the meter stuff we just talked about a minute ago, may turn out to be a really good way to do it. But in any event, we still need heavy storage applications at the point of generation, such as large wind farms. And you can see in the next curve here, called the California ISO duck curve, is in the middle part of this chart is the over-generation risk, where large gas turbine power plants essentially are scaling back so that they can let the DER resources onto the distribution grid. So one of two things is happening. Either they don't do this and there's no place to put the DER, so you really do need to store it, or if you do bring them back, you need a very, very heavy ramp up after 6 p.m., as you can see from this picture. And then that means the main generators have to be put back online unless there's a lot of storage capacity that can take up that slack. So this is a very demanding situation. So on this oversupply mitigation issue, essentially the market needs to automatically manage the oversupply. And it may do this in a number of ways, including changing the prices of the electric power. And we can see that in some of these ways of managing oversupply mitigation, we can increase demand by making the ISO's control area much larger. We can transition to more electrically powered vehicles, especially when they're sitting behind the meter and can be used as storage when they're not being used. Okay, they also increase consumption of power, which is something that's good at the right time of the day. Okay, we can change the rates, as we mentioned. We can dramatically increase energy storage, and we can let the ISOs control the power plants directly. This happens in some cases, but in other cases where there are large independent system operators, they don't have direct control of the power plants, and that needs to be changed. So in order to stabilize these grids, especially the ones that contain large amounts of DER, there's a number of things that have to be done, including automated frequency response. And usually very tight control around the 60 hertz or the 50 hertz number in the EU needs to be done. Otherwise, grid stability is going to be a real problem. And when there are unexpected events that interrupt the supply-demand balance, frequency control turns out to be a big issue. Now, on large steam turbine type equipment, it is possible that these grid forming elements are very effective agents in controlling frequency. The DER sources essentially have to turn into things that look like those machines. And as we'll see in a minute, real-time control can actually fix that problem. And so we know on the trend basis, certainly in areas like California and others, especially in Europe, where 60% or more of the energy production is going to become from renewable generators. And the grid is not going to be stable unless these renewable generators start behaving like large grid forming machines. And this can be done with real-time automatic control via firmware. So we make that point here. The regulations that control the deployment of DER are going to dramatically change over the next few years, so that the regulatory component on requiring power electronics to essentially simulate virtual synchronous generators is going to be the big thing that makes renewables much easier to integrate into large grids. And even in microgrid applications, you can see here on point 5 an example where some college campus buildings are driven by a local microgrid using PV, cogen, and battery banks. And the utility gas rates in this case go up after 2 p.m. So they run cogeneration wide open in the morning to charge batteries, and then switch the whole thing over to PV and batteries after 2 o'clock. Again, this is all local real-time control and has nothing to do with the larger grids. One component of this kind of real-time control is the usual high latency centralized control really doesn't work, which is the way a lot of it is done now. This is all going to change with distributed data buses that allow peer-to-peer interaction and extremely low latency. I'll spend a couple of minutes more on the storage requirements and energy storage systems. The packaging required for these things now is a mixture of containers. At the bottom, we have small modules like 30 kilowatt hours for residential systems. This is largely being taken care of by lithium ion right now, but that's going to change, as we'll see in a minute. And then we move upscale to 100 kilowatt hour modules, for industrial endpoints, megawatt hour modules for distributed network substations, and 10 megawatt hour systems for solar and wind farms. We'll show you a picture of one of those in a minute. Various technologies are in use now. Pumped hydro, that's currently in use and is being expanded in areas like California. Flywheels are going to dramatically expand, as we'll see in a minute. And then lead acid batteries are in constant use. These are lower cost systems, but they're just generally used for uninterruptible power systems and nothing too sophisticated. Lithium ion right now as sort of the battery of choice for larger scale installations and has the capability to do 1 to 10 hour ramps, like we showed on the California duck curve picture. So lithium ion was invented in 1985, won the Nobel Prize for Chemistry in 99, and has extremely high energy density. It's widely available. Its challenges, however, are flammability, real life cycle constraints. The number of cycles you can put through is dramatically limited. In vehicles, this starts to become a real problem at about 8 years of life. There are environmental issues with toxicity and recycling, extremely expensive to recycle, and global supply chain is very limited in ability to just continuously increase the production of these kinds of batteries. Here's a picture of the Tesla Big Battery in Hornsdale, Australia. $66 million installation for 129 megawatt hours of storage. Very good for this particular wind farm, but still a very high price point for this kind of storage. And we're trying to bring that down with applications like this one with flywheels. Flywheels have been used successfully for a number of applications for the last 10 years, but the cost has been too high and the sophistication of these systems unnecessarily complex. Here's an example of the sorts of thinking that's going on now. Prototypes have already been built of systems like this, where you have a very low cost carbon fiber flywheels with no axle. It's all virtual, magnetic levitation. All the complexity of these systems is really in the firmware. Very simple to manufacture these sorts of things worldwide and in low-tech manufacturing facilities. There's effectively no maintenance, and no one is sure why these essentially wouldn't last at least 50 years. So some quick conclusions. Over the last few minutes, we've been talking about trends in DER deployments, and as we can see, in order to increase deployment of DER, we just have to have distributed storage. There's no way around that. We need low latency controls for hybrid grids so that we can effectively create grid stabilizing machines using just DER and no classic grid forming machines like steam turbines. We need to use advanced storage concepts like extremely low cost flywheel structures like we discussed and others as they become available. And again, storage is the key to DER adoption. Thanks very much for listening to this discussion.